It's my great pleasure to attend this occasion to celebrate our fellowship and also the accomplishments of Gerhard. So it's my personal honor to have this opportunity to pay tribute to my thesis advisor. I'd like to thank the organizers for the invitation. So Art has made numerous accomplishments, and we just heard Mazur talk about his rational torsion conjecture, and the talk after me, Duncan will talk about his insight, which inspired the moonshine theory, and there are terminologies and mathematics which bear his name, like Grothendieck, arc, Shafarevich invariant, the Neron arc, Shafarevich criterion, and Arc's formula for the conductor of an elliptic curve. So what I would talk about is Arc's impact to modular forms and format encounter. The modular forms, well, classical modular form is a homomorphic function on the upper plane, and which has symmetry with respect to a convolution group of Z, and has a Fourier extension. And we study the arithmetic of the coefficients. So 20th century has seen an explosion of the progress in this area. In this talk, I will only mention a few which are relevant to the topic that I will touch upon. So first is in the 1930s, Hecke introduced the so-called Hecke operators associated to a prime, which acts on a modular form. Therefore, this reduces the study of modular forms to a common eigenfunction of the Hecke operators. And then in 1970, Atkin come up with a new form. It says that if we collect all this common Eigenhecke operators for a congruent subgroup of the special shape, gamma naught n, but for all the integers n. And then among them, it suffices to understand new forms in order for us to build up from them in a very simple way. So now the new forms theory is known for all the congruent subgroups of Z.
Okay.
And in 1967, Art published visual notes titled Modular Forms and a Dirichlet series. And this book is much appreciated by many people in the number theory. And in particular, at that time,
We don't have any microphone.
okay, thank you. So at that time, in 1967, Gade just published a very important result for his theorem, which gives analytic criterion for a function on the upper half plane with given Fourier coefficients to be a modular form. So I explained briefly based on the theorem in this book. Then I will mention a few his contribution in the 60s and early 70s to other parts. The first one is to number theory, to new form theory. So we take a new form, we can write it in its Fourier expansion. We assume it's a cusp form. And coming with the form, it has some parameters, the weight and the level and the character. And the leading coefficient A1 is non-zero. We can assume that it's equal to 1. This new form is a common eigenfunction for all the Hecke operators P, not dividing n. And the eigenvalue is the P Fourier coefficient of this new form. And together with the remaining APs for P dividing N, and they determine all the free coefficients of N. And this is expression is expressed in terms of the Dirichlet series associated to which has all the product. And we know that all these free coefficients are algebraic integers. And how big are they? For the P not dividing N, there's a famous Ramanujan conjecture, which was proved by the Lin in the early 70s, saying that the absolute value of AP is most twice e to the k minus 1 over 2. And so people usually pays a lot of attention to P not dividing N, but how about the P dividing N? What can we say about those APs? So that will depend on the character. So if a character chi is also a character of N mod P, then the situation is very similar to the Atkin type, that you know that AP up to sign AP divides N exactly once, otherwise it's equal to 0. And the new case is when chi is not a character of N mod P. So in that case, to determine AP, well, Arc has a theorem which was there already proved in the 60s. But in terms of operators, if you see it in right light, it tells you exactly that the AP has size P to the k minus 1 over 2. And another his important contribution to modular forms in the 60s as to convolution of L series. So if we take the two transforms, F and G of the same weight and the same level N, with free coefficients AN and Pn, then Rankine introduced the convoluted L series, is that we form a Dirichlet series using the coefficients AN and the conjugate of Bn. Then we complement this by incomplete zeta function. So Rankine proved that when N is equal to 1, then this L function has analytic configuration, also has a symmetry, satisfied function equation between S and the 1 minus S. And I've extended this to N square free. So to go from N equal to 1 to N square free, there's some hole to fill, namely there are primes which are dividing N, so we call that N primes. And there, to get a functional equation, one needs to know what are the vectors to fill in. And that's what Arc did. So he found the correct Euler vectors at that time. So he started the study of this Rankine L convolution. In general, then the whole thing was totally settled in the late 1970s. We can do this for any two new forms of any weight, any character, any level. So we know that to each new form, well, there's associated automorphic representation of GO2 over Q. So we have pi 1 and the pi 2, and we can take the cross product. So what this Rankine L function is exactly the global L function associated with 1 cross pi 2. And to find out this missing character is exactly to understand what's the local L and epsilon vectors in the representation theoretic. This was all. So this is the old part. Now we'll talk about the new part. So the new part it concerns the trace of Hecke operators. And this is an ongoing joint work with Bill Hoffman, Lin Long, and Gang too. So we are interested in an explicit formula for the trace of Hecke operators, PP, acting on the space of cusp forms if that group has cusp, or just modular forms if that group is co-compact and of a given weight. Okay. And that group is chosen to be a congruent subgroup. And the previous results in this direction are by Atkin for gamma 4, Atkin Ono for gamma 8, and Lefschetz Ono Nicholas for new forms for gamma 8, and the Lennon for gamma 3 and gamma 9. So in their approach, they all use a self-trace formula. So our goal is to express this Hecke trace in terms of hypergeometric character sums. So first, talk about the setup. So there are two kinds of groups that we consider. One is non-co-compact. So that is it's commensurable with SO2Z. That's the elliptic modular group that we are familiar with. The second kind is co-compact. It's commensurable with the one group, the maximum order of an indefinite quaternion algebra defined over Q. Because the quaternion algebra is indefinite, so we can embed this one group into the SO2R. So those cases, the group acts on the upper plane. So we look at the orbit of gamma in the upper plane. So it's a Riemann surface. If it's not compact, we can compactify by joining the cusp. That modular curve. And this modular curve or this Riemann surface can be defined algebraically. So we assume that the Shimura canonical model for this curve is defined over Q. Then we are interested in the modular forms, of different weights. Okay, so to each k, the weight will be k plus 2. So for each k, well, there is some kind of elliptic sheath, okay, so which is defined using the modular interpretation. So we have this elliptic sheath, we call that Vk gamma L on the algebraic points of the modular curve. Okay. So this was first defined when the group is torsion free and using the universal elliptic curves. If the group is elliptic modular or the principally polarized abelian surfaces with quaternion multiplication, if it's a quaternionic. So we first do this, then we, when the group is torsion, then we can choose the torsion free one, and we use the push forward to get a sheath for our gamma. Okay. So this at the beginning was constructed by the Lin when gamma is a converse group for SO2Z. So our idea is to use the theorem by Delin and Ota. So Delin did it for elliptic modular case, and Ota did it for the quaternionic case. So we interpret the trace of Hecke operator on the space of modular or transforms of a given weight of gamma as a trace of Frobenius at P acting on some cohomology space. The first cohomology space of modular curve and with coefficients in this sheet, elliptic sheet. Okay. So then this Frobenius trace part is a geometric way to realize the Hecke operator trace. And as a geometric setting, one can apply the Lefschetz fixed point formula. So we can rewrite the trace from the Frobenius part as a sum of the trace, Frobenius trace over points going through the FP rational point curve. So you take curve, you take reduction mark P, then you take the FP rational point. So what this means is that to understand the trace of Hecke operator on the space of transforms, what we should understand is that understand the Frobenius action on the each stalk. So here we are interested in the forms of even weight because odd weight space is 0. And so we have a lot of case to think about. And in this regard, we know that when the group gamma is a congruent subgroup of SO2Z, if we can look at the sheaf at the stalk, actually it comes from the K-symmetric power of the sheaf when K is equal to 1. In that case, it's a two-dimensional gamma representation. It turns out that for the quaternionic case, it's very similar. We also have this, except that there's extra twist by a character. But the upshot of this remark is to say that when we want to find out the trace of a higher and higher weight, actually all we need to know is what is the behavior when K is equal to 2. Once we know the trace for sin 2, and for the other higher symmetric even power, the trace there can be expressed as a polynomial of trace 2, sin 2. Okay. So then the whole idea is that we look at the V2 gamma, the K is equal to 2, this elliptic sheaf. We want to replace it. Another sheaf isomorphic. But this other sheaf, we can compute the trace of the Frobenius. Okay. And turns out that we could do this for the group gamma of a special type. And this type, they are all the triangle groups. Okay. The triangle groups is a way to describe a group. You see that you always see 3 entries, like 2, 3, infinity. So this means that a group is generated by 3 elements. One is square is equal to identity. The second generator cube is equal to identity. The third generator is torsion free. And with one relation is a product of 3 generators equal to identity. So if I look at 2, 3, infinity, if we look at its fundamental domain, it tells you that it has 1 cusp and 1 elliptic point of order 2, 1 elliptic point of order 3. That tells you that group is PSO20. So likewise, if I do infinity, 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 such a group with 3 cusps and no torsion points, and that group is gamma 2. So the groups we consider will be like gamma 2, gamma 3, gamma 2, PSO2Z, gamma 2 plus, this is gamma 2 together with the convolution at 2, this mentioned in Barry's talk, and also gamma 3 together with the convolution. So all the groups on the right side should be viewed projectively modulo the center plus minus 1. And to me, the more interesting part is the co-compact case, where we have group is 266 and 246. So that means there's no cusp, has 3 elliptic points with order like 2, 6, and 6 respectively. Okay. So to each of these groups, we can find a suitable twist of the hypergeometric sheaf constructed by cats. Okay. So with that, we can find out the explicit expression for the trace of the Hecke operator. So let me first talk about example of the case of SO2Z. But we know that in this case, the modular curve is the J line. And there are 3 bad points at infinity and at the 2 elliptic points, which have J coordinates 0 and 1728. So if we remove these 3 points from the modular curve, on the remaining part, then it is very nice. So on top of each point J on this J line, well, there is an elliptic curve explicitly defined with this equation involving J in its coordinate. And as J moves, we get a family of elliptic curves. So this is called a universal elliptic curve over this open set X0. And so we can apply the same procedure to come up with the sheaf using the elliptic curves that with specially chosen elliptic curves given by this equation. and call that sheaf FL. And if we have a congruent subgroup gamma of SL to Z, then its modular curve is a finite curve of the J line. Then we can put the sheaf back to the modular curve. So we get a sheaf on the group gamma. And the wonderful thing is that Show in 1988 showed that for the case K, even at least 2, then the sheaf we originally put, which I call automorphic sheaf, is isomorphic to the K-symmetric power of this specific sheaf that are defined using specific equation. Okay. So this means that if we have explicit curving map from the curve X gamma to the J line, then we can use that express information to compute the contribution of the Hecke eigenvalue. So if we do this at a point which is neither cusp or infinity, then we just use this equation of the elliptic curve that's explicitly given to compute its AP. And at elliptic points, and to compute the contributions from there, the Tate's algorithm and the neuron arc Shafarevich criterion are used. So that's where we see another occasion where the arc's contribution comes into play. So similarly, for like gamma 2, gamma 3, and the gamma 2, one can also find this kind of explicitly defined the elliptic family outside of the dead points, and we can do the same thing. It turns out that after you get this formula, the contribution can also expressed by hypergeometric character sums. So now let me go to the hypergeometric sheaf that Katz constructed. So to construct a hypergeometric sheaf, we need a hypergeometric datum. Okay. Well, a hypergeometric datum means that we have 2 strings of non-zero rational numbers of the same length. The first set has A1 to AN, the second set B1 to BN, B1 to B. Here we assume that this datum is primitive. That means the difference between AN and BJ is always not zero. Sorry, it's always non-integer. Now, so to this hypergeometric datum, we are going to associate 2 kinds of things. The first is the complex analytic. Okay, so that is the standard hypergeometric function that one sees classically with variable lambda in the complex. Okay. So this hypergeometric function satisfies the Fuchsian differential equation of order n, and with 3 singularities, which usually we normalize it to be at 0, 1, and infinity. And the solutions at any non-singular points will form a local system. The solutions at all the non-singular points form a local system and give rise to a monodromy representation of the first fundamental group of projective line with the 3 points removed. Now we come to the algebraic side. So with this alpha and the beta given, we look at this AI and the BJ, we look at denominators, we take the least common denominator as ordered n. Then Katz will introduce an Elliptic rank n hypergeometric sheaf. Okay. And this hypergeometric sheaf is defined on the group GM. Okay. And with explicit action of the Gauss group over the absolute Gauss group of the cyclotomic field, joining n through 1. So in a very special case, if this datum is defined over Q, then this CAS representation can be extended to GQ. So there are several extensions. One of them is done by Boykers, Cohen, and Malit, which we call a BCM representation. So we favor this representation because this representation gives us the explicit trace. So it's a trace, it's as follows. So if we look at a point, say lambda, which is non-zero rational number. So we look at action of a Frobenius group GQ on this block, and the BCM gives you the trace at the Frobenius P at almost open P. And you see that explicitly. So the first part is a sign ±1, and we know explicitly. Then followed by √1, which we also can compute it. Okay. So then finally, we have this hypergeometric capital sums, which they define. So this hypergeometric capital sums is defined as a product of a Gauss sum. Because the definition is a little bit long, so I would spare you of all the details. So it's defined using the AIs and BJs. So we have this type of hypergeometric capital sums. So the BCM representation has explicit trace at the Frobenius P. So in the future, when we have the hypergeometric sheath attached to hypergeometric data, then if the data is definable Q, we will always assume that we extend it using the BCM representation. So here's our main result. So this gamma be one of the 6 groups. All of them are elliptic modular, and then plus 2, which are 2, 4, 6, 2, 6, 6. So then given even K and these 2, we want to compute the trace of Hecke operator TP on this space of Cus forms. We can, as we explained before, using the theorem of Filling and Ota, this is the minus of this trace can be expressed as a trace of Frobenius on over the points of that curve, P rational on the curve. So the key point is to express this Frobenius trace lambda. Okay. So to express them with their different kinds. Okay. If this lambda, well, is neither a elliptic point nor a cusp, then we can express this trace using the values of the hypergeometric character attached to a datum, and this datum, the choice depends on the group, which I will give you. And the contribution from the lambda corresponding to the elliptic points will be the same datum, but with value at 1, and together with some Jacobi sums. And then if it has cusp, then each cusp will contribute 1. So here is the corresponding datum we see for each group. So as you can see that here, 246 and 266, I use the same datum. But actually, this datum is associated to 246. And the sheaf on 266 is a pullback on that on 246. So I just use the same here. So I would like to give you an example for the Quaternionic case, 246. Because we know that if we see a module form for the Quaternionic group, if we view them as holomorphic function on the alpha plane is very difficult to compute the Hecke trace because there's no Fourier expansion. So that now here, in this theorem, our theorem tells you what is the trace, or Hecke trace on the full space. So let me explain a little bit of the group. There's 2, 4, 6, and 2, 6, 6. They all come from the group 2, 2, 3, 3. So they all come from the very well studied Quaternion algebra with discriminant 6. It's indefinite Quaternion algebra over Q defined by 2 elements, I squared to the minus 1 and the j squared equal to 3, and the anti-commute. It has a unique maximal ideal up to conjugacy. And that the node 1 group, we take it as we count on node 01, as we said before, we have a very explicit basis. And when we look at it on modulo the center, well, that's the group called 2, 2, 3, 3, because its fundamental domain has 2 elliptic points of order 2 and 2 elliptic points of order 3. This group 2, 2, 3, 3, well, is normalized by Atkin Maynard involutions. One is we call it W2, one for W3, the other one W6 is W2 times W3. So 266 is obtained from 2, 2, 3, 3 by joining one involution, W3. And if we put the 2 involutions, W3 and W2, then we get a group 2, 6. And the algebra formed by the order modular forms for the group 2, 2, 3, 3 together is a polynomial ring over C generated by 3 modular forms of weight 4, weight 6, and weight 12. This much very similar to SO2Z, except that in this case, these 3 generators satisfy one relation. This weight 12 one, that one squared plus 3 times the weight 6 to the 4th power, so H4 to the 6th power equal to 0. And if we look at the 3 generators, each of that is an eigenfunction of W2 and W3. And we know the eigenvalues, as we can see here. None of the generator is fixed by both W2 and the W3, which means that none of the generators, well, are forms for the group 2, 4, 6. So here, the example I want to give you is to consider the case exactly the group 2, 4, 6. So when we look at this group and we look at, well, what is the lowest weight, the first weight for which the module form is non-trivial, and that weight happens to be 8. So the forms for the group 2, 4, 6 are the forms from 2, 2, 3, 3 that are invariant under both the W2 and the W3. So with eigenvalues here and generators there, we see that very clearly. So you find out that the weight 8 space is one-dimensional, generated by H4 squared. So that for this particular form, then we can apply our theorem. Okay, so our theorem tells us that if I look at the Hecke eigenvalue of TP on this space, which means that on this form, and that trace is exactly the eigenvalue of H4 squared and the action of TP. So we can express that eigenvalue explicitly in terms of the hypergeometric sum. Now, in this example here, the module form has weight 8. It comes from K equal to 6. So we know that sim 6, well, can be expressed as sim squared the trace of sim 6 can be expressed using trace of sim squared as a polynomial. So that's the polynomial. Okay, so we first find out what is the trace on W2. That we can express in terms of hypergeometric sum. And then when we go to the weight 8, so for the point, which doesn't come from the elliptic point, we have this very explicit expression in terms of the trace, Frobenius trace on the V2. Then similarly, also for the contribution from elliptic point of order 2, we use this the hypergeometric sum at the point at value at 1 here, squared minus p squared times p. And then the remaining part is a contribution comes from the other 2 elliptic points. So we get a very explicit expression. And we also know that correspondence tells us that for this from H42 on the quaternion group, will correspond to weight 8, level 6 new form for the group gamma naught 6, and which has eigenvalue under W2 and W3 there would be minus. Okay, so that form, well, we can find out. And so this expression also tells us the Hecke eigenvalue for the corresponding 6,888 form. And actually, we use this to check that our formula is correct. Okay. So then I want to say a few words about the Shimura curves. So the Shimura curves are first studied by Shimura and a bunch of many people, like Arg also studied quite a bit on the Shimura curves. And our friend Jordan here also did it, Keys, etc. So there are many people who did that. But for our specific curve, we're going to follow the one by Barbara Max. So this particular curve of 2233, well, it's a Shimura commutator model has equation that explicit x squared plus 3y squared plus z squared equal to 0 that comes from the identity of the modular forms that we see here. So it is a curve of genus 0 defined over Q, but doesn't have any Q rational points or any real points. Then the action of the involution W2 and W3 and W6 is also explicitly expressed in terms of the coordinates by changing one coordinate into minus while keeping the other 2 fixed. And the W2 has 2 fixed points. Okay. And that 2 fixed points are the 2 elliptic points on the curve with order 2. And then likewise, the 2 fixed points of W3 are the 2 elliptic points on the curve 2233. But the W6 also has 2 fixed points, and that, well, they are not elliptic points. And the curve attached to 266 is the quotient of the curve for 2233 by the action of W3 itself. Is a projected line over Q. So at the projection is also very clearly expressed in terms of the coordinates by the linear X. And one can also check the image of the this W2, W3 under this projected map. We will find out that the 2 fixed points of W2 will send to 1 point. So that's the elliptic point of order 2 on the curve 266, and it is Q rational. And the other 2 points of order 3 on the curve 2233 has image Q rational, but in the quadratic extension, join square root -3. So that's the 2 elliptic points of order 6. So for this curve 266, we look at the elliptic points, only one is rational, the other two are not Q-rational. And again, when we take a curve 266, mod out that by the motion W2, we get a curve of 246, and which is also a projective line over Q with explicit map. Now this time that we find out that the three elliptic points on the curve 246 coming from the fixed points of W6, W2, and the W3 back to the 2233, they all have Q rational points. So that means that on the curve graph attached to that 246, all three elliptic points are Q rational. And that setting is suitable for us to do the H sheet. So then in that case, we define a data, and then we do have the hypergeometric sheet. The 266, we cannot do it because the hypergeometric sheet, the 3 points are always Q rational. So, but on the other hand, the curve 266 itself, well, we can give it another Q model to make the 3 elliptic points Q rational. Let's call that new Q model X twiddle. And certainly this new model is isomorphic to the old model by a map which is defined over quadratic extension. So for the model where the 3 elliptic points are Q rational, we can associate a datum which is defined over Q, and we do have a hypergeometric sheet attached to that. So now what do we do for the 266? Only one elliptic point is rational. So, but we have this explicit projected map. So we pull back the sheaf on the 246 to the curve on 266. That's the sheaf we use. Okay. So what is the relation between that sheaf and the sheaf that we can define using the data? Okay. So that means that if we go back, so on the twiddle curve, we have this hypergeometric sheaf. So I can pull back by this C to a sheaf on this X266. And that sheaf I compare with the sheaf I use, I find that the action of the Galois group over the quadratic field, Q joining through 3, they agree. But but the extension to GQ, they do not agree. So it's a 2 different kinds of sheet. So finally, let me give you a sketch of the theorem for this case of 246. So as I said at the beginning, so to compute the trace for the module forms, well, it boils down to understand what is the Frobenius contribution for the automorphic shift of D2 before 6. So we want to compare that with the hypergeometric shift. Okay. And the idea is that to find the rank 1 sheet, to twist it so that the 2 shifts are isomorphic. So how do we find this rank 1 shift? So the first is to look at the counterpart of the elliptic sheaf, namely the sheaf over the complex. So we compare so over the complex, we have the complex sheaf. One is coming from this automorphic construction. Another one is associated to the hypergeometric function attached to this special datum. But we twist it by multiplying by 1 minus t to the 1/2. Okay. Then we compute the local monodromy of both sheets at the 3 elliptic points, okay, and to show that they agree. Then we use Katz's rigidity theorem to conclude that the 2 complex sheets are isomorphic. Okay, So it's easier for the complex sheath to be isomorphic. But the complex sheath gives us idea how to modify the elliptic sheath. Okay. So first of all, there's this extra 1 minus t to the 1/2. The elliptic side means that well, we were twisted by a rank 1 sheath. So at each stop, it's a quadratic character. Okay. That corresponds to this 1 minus t to the 1/2. So then we go back to think about this, the cat sheath. Cat sheath originally, when it was constructed, it's not that, it doesn't have the action of GQ, but has action of Gauss group over cyclotomic field. In that case, the cyclotomic field is joining 12 to the 1. So this field is a biquadratic extension of Q. And we need an extension to GQ, we chose the BCM representation. So now we want to see, well, whether we need to adjust that choice. To see that we just compute the determinant of the automorphics on the Gauss action on the automorphic side. We find out that it's cyclotomic character cubed, and compute the determinant on what we have now. Find out that they differ by a quadratic twist. So that means that we should further twist the BCM representation by the quadratic character on each stop. Okay. So finally, so this is what we use the complex sheaf to find out one piece, and we use the determinant to find out the other sheaf. So now we want to say that, okay, now that's it. We found, this should isomorphic to what the automorphic side gives. And to show that, we will need to compare the both downward actions at Q rational points with the CM, which are not electric. So after that's done, then we can conclude that the sheaves do isomorphic, because when they are complex sheaves like the isomorphic, that means the elliptic sheaf will differ only by a character. Then we pin down the character by comparison of the action at one stop. Okay. So that gives us the contribution from the non-elliptic points. Then there's a contribution from the elliptic points. Okay. Fortunately, in this case, each elliptic point is represented by a billion surface, and that surface, and it decomposes the product of two elliptic curves with a CM. And so the computation there, well, it's made easier because of this splitting into elliptic curves. So we can adapt the Show's algorithm. Okay. So that's all. Thank you very much for your time. Next one, the message.
Any questions?
Yes.
When you were speaking of the J line, you described one elliptic curve over very different from zero. There are many such curves. You can twist them by some. So can you characterize which it is as a modular and the particular elliptic curve?
Which case are you talking about?
J line.
A J line. I do not know. I just took the what show did it. I'm sorry.
And there was similar questions for the quaternary algebra. Then still there's minus one, the multiplicative. So how do you get a complex local system on the course?
I mean, we only consider the even weight case.
Yes, but you start with the rank 2 local system. You have something even geometric.
Can I talk to you tomorrow?
Yes.
I have more questions to ask you.
Because we're on a tight schedule.
Yeah.
Let's pause. We can ask. We need questions at key. Let's thank her again.
Thank you.
And we